Eruption 75,000 years ago has helped people spread around the world. The eruption of the Toba supervolcano, which took place around 75,000 years ago. It is considered one of the largest known volcanic eruptions on Earth. According to recent research, it may have helped our species spread around the world. It is assumed that the explosion of the Toba supervolcano in Sumatra, Indonesia, was so powerful that it caused a volcanic winter that could last up to 10 years. The resulting cooling of the climate could have lasted much longer, up to 1,000 years, although exactly how long is the subject of disputes in the scientific community. The eruption occurred approximately 75,000 years ago, and in the place where the volcano was located, there is now a lake of the same name. In a new study, scientists speculate that this eruption may help answer the question of what caused humans' eventual expansion out of Africa. The results and description of the research were published in the journal, Nature. The story of our species leaving Africa is incomplete. Most likely, people left Africa many times. But it is believed that the main stage of migration took place less than 100,000 years ago. A popular idea is that humanity left Africa at a time when food was plentiful and human populations were expanding. However, in new research, a group of scientists presented a different view. According to them, people may have left Africa due to scarcity, in search of better places to live. The main suspect in causing the lean years was the Toba supervolcano. The Toba eruption may have changed the environment in Africa, but humans adapted and survived the change, said Curtis Marine of Arizona State University. According to the researcher, the behavioral flexibility of these people not only helped them survive the super-eruption, but may also have facilitated the subsequent dispersal of people to the rest of the world. Scientists studied the Shinva Metama 1 site located in the lowlands of northwestern Ethiopia, along the Shinva River. Archaeological research shows that the Toba eruption occurred when the site was inhabited. Stone tools, traces of food preparation, and even the oldest evidence of the use of the bow were discovered at the site. Tiny pieces of volcanic glass were also found, the chemical composition of which corresponds to material from the eruption of the Toba volcano. The research team used new methods of cryptotephra analysis developed for other studies. Cryptotephra are tiny shards of volcanic glass measuring 80 to 20 microns in size, which is smaller than the diameter of a human hair. Extracting them from archaeological deposits required extraordinary patience and great care. Analyses of artifacts, including mammal teeth or ostrich eggshells found at an archaeological site in Ethiopia, indicated that this place was inhabited during long dry seasons, when rivers dried up and water reservoirs shrank. Scientists speculate that as water reservoirs shrank, local residents more often hunted animals that came to increasingly rare watering holes, and fishing without special equipment became easier, which was reflected in their diet. But over time, of drought-depleted game and may have prompted people to migrate in search of more food and water. As food and water supplies ran out during the dry season, people were forced to move to other places, said John Kappelman of the University of Texas at Austin, lead author of the paper. Periodic rivers then acted as pumps that sucked up populations along the banks of one reservoir to transfer them to another. This could potentially disperse people out of Africa, he added. It is unlikely that the inhabitants of Shinva-Metama I left Africa. However, the behavioral flexibility that helped them adapt to the harsh climatic conditions following the eruption of the Toba supervolcano was probably the key human trait that allowed our species to eventually spread around the world. Investigations of a settlement near the Shinva River also provided evidence of the use of the bow. The most characteristic artifacts found at the site are small, triangular objects that were most likely arrowheads. Bones of antelopes and monkeys with traces of processing and traces of fireplaces were also found at the site. Human brains have been getting bigger for several decades. Our brains are getting bigger. In a study conducted by Californian scientists, participants born in the 1970s had 6.6% larger brain volume and almost 15% larger brain surface than people born in the 1930s. Scientists believe that larger brain size may potentially reduce the risk of developing age-related dementia. In their research, they used the Framingham Heart Study (FHS) database, which has been collecting data since 1948. The database began as a project collecting data to assess patterns of cardiovascular disease and other health problems among the American population. In the first stage of the study, 5,209 people aged 30 to 62 took part. The study has been running for 75 years and now includes second and third generations of participants. But the database also collected data from brain magnetic resonance imaging. Researchers from the University of California, Davis used brain scans conducted between 1999 and 2019 on FHS participants born between the 1930s and 1970s. 20th century. The data concerned 3,226 women and men, whose average age at the time of the study was 57 years. The results of the analysis were published in the journal JAMA Neurology. The decade in which we are born appears to influence brain size and potentially long-term health, said Charles DiCarli of the University of California, Davis, co-author of the study. Genetics play a major role in determining brain size, but our findings indicate that external influences such as health, social, cultural and educational factors may also play a role, he added. California researchers compared brain scans of people born in the 1930s with MRI results of people born in the 1970s. The analyzers showed gradual, steady growth in several brain structures. For example, measurement of brain volume, intracranial volume, has shown a steady increase from decade to decade. For participants born in the 1930s, the average volume was 1,234 cubic centimeters. But for those born in the 1970s, the volume was 1,321 cubic centimeters, or about 6.6% more. An even greater increase was seen in the brain surface area. People born in the 1930s had an average brain surface area of 2,056 square centimeters, and study participants born in the 1970s had an average brain surface area of 2,104 square centimeters. This is an increase of almost 15%. By comparing the brain scans, the researchers saw that other brain structures also enlarged, such as white matter, gray matter and the hippocampus, an area of the brain involved in learning and memory. While conducting research, scientists wondered what bigger brains could give us. They hypothesized that increased brain size may lead to increased brain reserve, potentially reducing the overall risk of developing age-related dementia. The most common type of dementia is Alzheimer's disease. In the United States alone, approximately 7 million people suffer from it. This number is expected to increase to over 11 million by 2040. While these numbers are impressive, the incidence of Alzheimer's disease, or the percentage of the population affected by it, is decreasing. Another research team found that the incidence of dementia has been declining since the 1970s. The larger brain structures observed in our study may reflect better brain development and better brain health. Greater brain structure means greater reserves and may be a buffer against age-related brain diseases such as Alzheimer's disease, DeCarli said. A surprising arrangement of oppressed feet. In nickel-cobalt-chromium alloys, nickel atoms can arrange themselves into regular patterns under pressure, simulations by an international team have shown. Until now, it was believed that such orders could only be formed under the influence of thermal treatment. Scientists from the National Center for Nuclear Research predict the possibility of organizing the structure of atoms in multi-component alloys using point pressure on their surface. Efforts are underway to confirm the numerical result experimentally, representatives of the institution said in a press release. In standard modeling of metal alloys, it is assumed that the atoms of various elements constituting the alloy are randomly distributed in the crystal structure. At the same time, the existing short-range areas of order in the chemical structure of alloys, CSRO, chemical short-range order, covering several or a dozen interatomic distances, may be the source of key properties such as exceptional hardness, strength and plasticity. This is because ordered structures can hinder or even prevent the movement of defects in the material structure. By simulating an instrumental hardness test of a nickel-cobalt-chromium (NiCO-CR) alloy, A team of scientists from the NOMATEN Center of Excellence at the National Center for Nuclear Research was surprised to discover that nickel atoms can arrange themselves into chemically ordered structures as a result of such a process. Similar phenomena have so far been observed only under the influence of thermal treatment. But simulations have shown that point pressure with a diamond blade indenter is enough to achieve the effect. This result is so important that an article describing this achievement was published in the journal Physical Review Letters in March. In this study, we used computer simulations to check how certain thermal treatments and nanomechanical sampling techniques affect the arrangement of atoms in multi-component alloys. In particular in the NiCO-Cr alloy, explains Hossein Nadi, the first author of the publication and a PhD student at Co-Nomaton, quoted in the release. We discovered that certain specific instrumental hardness testing methods can induce local reorganization of atoms under the indenter tip, leading to unique periodic structures in their density, he adds. Molecular simulations were based on known and repeatedly verified versions of interatomic potentials. The modeling began with computer heating a sample of the NiCO-Cr alloy with randomly distributed atoms of individual components in order to obtain a realistic initial state. Then, as part of the simulation, a diamond blade was pressed into the sample. After reaching a certain depth, the process was stopped, leaving the indenter stationary in the sample. In this state, the changes occurring in the material were simulated using hybrid molecular dynamics processes and Monte Carlo methods. It was discovered that under such conditions, nickel atoms separate from cobalt and chromium atoms, as a result of which they are no longer randomly distributed, but organize into a system of layers spreading under the tip of the indenter. Importantly, this pattern remains in the alloy structure even after the indenter is removed from the material. However, the pattern does not appear if the phase of prolonged force application is omitted, i.e. during the normal process of pressure and its immediate release. Our findings provide insight into the possibilities of manipulating the properties of alloys at the atomic level, which may impact the design of materials with given parameters for various applications, adds Hossein Nadi. In the future, the group wants to focus on combining experimental hardness testing with high-resolution electron microscopy, HRTEM, to further verify this phenomenon. Future research may determine whether the observed atomic distributions have an impact on the properties of the tested alloy that are important for applications in materials design and engineering.